do everything. So we'll go for the unit only. Then these are actually in TensorFlow it is available. If you go for the higher models, also some of the, actually they have added the Deep Lab V3. This one actually one of my friend already used, he used the for the kidney segmentation. Another of my friends, so the Deep Lab V3, it also gives very good accuracy. But unit is the most popular and evergreen one. And if you go for the backbone, for the feature extraction one, which can we, along with unit, we can work, because unit for segmentation. So some CNN models would we need also for feature extraction. That one is VGG, ResNet, ResNext, SE ResNet. These are the models I just made on a table that can work as the backbone or the feature extractor. Now, if you go for our segmentation model creation, of course, we have a demo today, but what are the simple steps we need to follow? First, you need to prepare your data set. You need to import your required classes and function. Then selection of the segmentation model. Selection of the segmentation model means you need semantic segmentation, instance segmentation, or panoptic segmentation. If semantic segmentation, then what model you need to use? UNet, FPN, or PSPNet, all those models, because every model has some advantages and disadvantages. That also we always go for a, you can say, literature survey, so that you need to decide. And selection of the backbone network. Backbone means for the feature extractor. There are many classifiers are there. Which one is suitable? That also you need to go for either experimental way, or maybe hit and trial way, or maybe some literature way. Then we go for the model fitting, training, hyperparameter tuning, then finally model prediction. So these are the common 8 steps generally we follow. Let's go for the first step, preparation of the data set. Okay, so you have some input and then you have give to the semantic segmentation model. So some input, sorry. So what's that input? In the segmentation, like in the detection, we have seen the inputs are what? The image and the corresponding bounding box, that XML file I have generated using label IMG. Like this, in the segmentation, we have two things. One is the image, and we generally call the corresponding mask. Just like in detection, we have the bounding box. In the segmentation, generally, we are giving a mask. Means this part is the infraction. But how machine will know this part is the infraction? The machine needs to train, because training is going on. When the training is going on, we need to give this mask. But for the testing one, you don't need to give any mask. Okay. After once the model is well trained, you just only need the image. Give the image, the machine will predict itself. But for the training one, you need to give the image as well as the label. Then how the label is generated, that one also we need to check. Okay, so that part I will show you how the label is generated. For that one, we have one software generally we use. This is Label Me. The last one we have used label IMG. We'll go for Label Me. Oh, it is already open. Okay, then I'll just label one. Maybe I'll go for this one. Let's say I'll go for this one. And then I want to segment this part. Okay, so how to do this one? We'll just take polygons for here, create polygons. Then we need to give dot. I don't have mouse, so it will take some time. Like this. You need to give a name, is it? Okay, so here it is actually the label. We can move to the next image. Sef. Okay, then we can move to the next image and do like this. This also there is some another. Suppose you want to do a rectangle one, also you can do edit, just maybe create a circle. Suppose you want to give just not that type of, you just give a circle. You can also give a circle type of those things. Maybe in fact, two. Just in fact another one. Oh no. Okay, just like you can give the label. So this one actually for the segmentation one. So when we see what kind of label already been there, if we will check, it is actually gives us a JSON file. If you will open it, it is actually a JSON file. And here you can see our label is in fact, and these are the points, the coordinate of the points, the points we have given, these are the coordinates. It is there. And the shape type is polygon. If I didn't save the circle one, if I make a circle, then it can take a shape type of polygon. So in this way, we actually generate the JSON file. Then we have a piece of code. We'll give the image and their JSON file together to generate this type of mask image. This mask image. So this mask image, we cannot generate it directly. We need to give this image and the JSON file generated together, because that Python program will check this with this image and the corresponding the mask file. The JSON file, this images corresponding JSON file, then together in that code, it will generate this mask. So there is another also intermediate step, but final input is this image and the corresponding mask. But before this corresponding mask, there is one JSON file is there. And how this JSON file is generated, you have already used label me to generate this file. I have already used this one. We have already generated the label. So from that one. So generally we use this one for labeling or create the annotation one. So after the annotation has been done and you have already created your mask, now we will divide our training and testing data set. Generally, we are giving images training, then corresponding mask training, then images testing, then corresponding mask testing. Means training images and its corresponding mask, then testing images, then it is corresponding mask we are giving. So you can ask me why you in the testing also you are giving the corresponding mask, because generally for the manuscript purpose, when we need to show for our testing data, what's the accuracy we are got. So we need to give one, we need to have some comparison parameter. So after our model is predicted, okay, this is our IOE or this is something, then we can compare it with our mask. Then it can have its own output and the corresponding marks. It will compare whether it is the correct segmentation or no. So some kind of quantification of your outcome we generally use for mask. But even if you are just giving only the image, that also fine. But for the training one, we need the training and the corresponding mask. So from the image and the corresponding mask, the machine will train what are the segmentation parameter. That's why just I mentioned it is optional, only required for the performance evaluation. So this is like one example. If my folder is dataset one, and inside this I have one folder images prepared train. Here I have my brain images. Then I have my corresponding annotations. Then I have for the testing one, these are the images, and this one is the mask corresponding to that. So now our dataset is ready now. Now we need to import the classes and function. This one is like something you need to like for the optimizer, for the loss function. This part we have already discussed in our classification class. So we need to import those parameters. Then we need to call our training and testing data. So here like I have my some folders name like variable name from the train image. I have my dataset one folder, and here my images, train images, then train mask. I have my annotations, then I call the test images and the test mask. This is the path of the training and testing image data you need to specify. Then the number of classes, like how many classes you want to segment. For example, you need to mention number of class 6, 2, 3 based on your application. For example, here I want to classify infract. So here my number of class is equal to 2. Why my number of class is equal to 2? You can ask me, because infract is one class and always background is always another class. Generally for the semantic segmentation, we always give one, whatever our class we want to segment, always plus one. And we always dedicated one class to the background, so that apart from our class, what we want to segment, the machine should know the rest part is the background. So that's why we give another class as the background. So apart from the label, we have already trained you, we have already given you the rest are background. So generally we give two class. You give n plus one class if n is our total number of classes. Let's say we have the number of classes 3, then we want to like segment like this person and the bicycle, then person 1 class, bicycle 1 class, and background 1 class. So total class is 3. So this is some kind of like how many number of classes is very important, you need to specify. Then how if you'll keep the 1 class, 2 class, 3 class, how machine will actually learn the thing. One student asked me, so I have added these slides for that, how machine will learn based on your segmentation, because this is your mask we have just generated using label me. So this is our input image and this is the mask. We want to classify the person's spots, plant or the grass, this part, sidewalk, the roads, and the building structures. Okay, and we give a different color to each classes. So here how machine will, in this image, how the machine will learn based on this one. You see the person, the part where person is there, the amount of pixel, the machine will learn 1111. The purse is the purple color, this one is 222. And the sidewalk is which color? 4. Here see the sidewalk is 4. And the tree and those are the plant and grasses is the green color. These are the 3. And the building and the other structure are the 5. So the machine from this, when we give to this label to the machine, the CNN model, which will helpful for our feature extraction, the machine will learn from this actually. Then it will extract the features from those parts. Then how, like if you want image, how the machine will, one hot encoding we will go. So how the machine will learn. So it is like for one image, it will have each pixel has certain label, and it is like number of classes. Let's say we have 5, 1, 2, 3, 4, 5. Then one image, it is divided like this. First, it will like the person, then the images, then the pixels. It will make one of the next segmentation, like the posh is our 2, the rest are 0. In the third, what we have the grasses, then whatever wherever the pixel is there, it will make it 1, rest are 0. Like this we have the sidewalks and the other structures. So it's just like it will learn like this. For one image, it is divided into number of classes, like it will learn like this. It will divide the entire pixel in such a way that so that it can know, okay, because it will give the shape and size. In this image, in those pixels, actually the sidewalk is present. In this image, in that pixel, the building is present. Here the sidewalk is present. Here the grass or the tree is present. So in that way, because machine is a dumb, it is like only can know 1 and 0. It is not like human eye. It can know some color or something. So for us, it is green color, or for us, it is some color. But for machine, it's just like 1 and 0. So machine can understand in such way that. Then we go for our, because I have already mentioned in segmentation, we have 2 part. One is encoder part, one is decoder part. So encoder part just help us for the feature extraction. When we give these things to the machine, someone is there to extract those features from that, like how we can know this is a grass, how we can know this is a tree, this is a sidewalk and how much it is present, how we know this is a person, what is the shape of the person, how it looks. So someone is there to from extract those features from this part, this part, this part, and this part, and that's the responsibility of CNN. We need CNN for that. And the decoder part, to some after the feature extraction, someone need to segment that part. So that one we call as the decoder part, where we are using UNet as the segmentation model. So here our training and testing data. Then we have already considered the number of classes. That part we have already discussed. Then we call the VGG unit. Why I call this is the predefined function VGG unit. Here is just like unit is the function, and as we are using VGG for the feature extraction, so the name is VGG unit. We have also, if someone is not wants to use VGG 16, then they can call ResNet 50, another extraction model, or someone can use MobileNet. The demo I'm going to show you is also using EfficientNet. So, or someone is not don't want to use UNet, then they can call it VGG PSPNet. That is another model. So some predefined functions are already there. You need to call those functions. Then inside inside that function, what you would like to mention, the number of classes, how many classes you want to segment, and your input height and width of your image. Then you will call your model where like unit is the number of classes, get VGG encoder. So the model name is, you can give VGG unit or anything. Then we will go for this one. The unit is the model we have just discussed out because you are using unit for the segmentation. If you don't want to use unit, you can use PSPNet, SegNet, FCN, FCN 8 layers, FCN 32 layers. So these are some segmentation model you can directly call here. The next one is the get VGG encoder. Get VGG encoder means you will create you will extract those features using the VGG, which acts as the encoder. If you don't want to use VGG, you can call get ResNet 50 encoder, get MobileNet encoder. Here, like the in this GitHub, you can get all the model name from there. Then what is that VGG encoder? If we want to see the code, then inside that get VGG encoder, this is the function, the definition here we can see, or because the VGG is the 5 convolutional layer, and last time we have discussed, as we are only using VGG for the feature extraction, we no need the prediction layer. So the dense layer we have already got. So then how many block we have? 1, 2, 3, 4, 5. So how many block? Here you can see this is the first block, 2 convolutional layers, convolutional 1, convolutional 2, then our pooling layer, then we have some features, we store it at X. Sorry, store it as F1. Then we have second 2 convolutional block and 1 pooling block, then we store it at F2. Then we have 3 convolution, 1 pooling, then we have make it as, we store it as F3. Like this, we have 5 convolution, then we have written, they store it in like an array, all the features along with the image input. So this one we are now encoding part, we have extract the feature, store it in an array, and now give it to the decoder part. The decoder part, what it will do, we are using the decoder part in the unit. So the unit is nothing but it is like some combination of layers. So what it will do, it will take F4, then like I have only mentioned here F4. For the other layer, you can also other like features you can also pass, that no problem. For example, there are many layers and finally you can pass, then it will return the model. So this one is actually your segmentation model, because last time when I have explained you this layers concept, it that much boring for you. So when we will do the real implementation, we'll discuss about why we need upsampling, what the necessity of concatenation, what is the zero padding. That one is much important, but this one you can now know. Okay, in the decoder part, we have also certain layers which can help us for the segmentation based on the features we extracted from our encoder part, which one is the BGG16. Then after the model is trained, then we have now the model, all the features already segmented. Now our segmentation model is ready. Now we go for the training. Then for the training one, what we need to do? We need to declare this model because we need to pass the model. The model is already trained. The model is already learned the feature. The model already segmented the feature. So we pass the model. Then our train images, then the annotation, then we need to mention some hyperparameter like epoch, the batch size, the optimizer. So all those things like it's some kind of hyperparameters we need to put for our training one. Like this one I have mentioned, like the optimizer, learning rate, the loss, and all those parts that we have already discussed. Then we need to fit our model. Fit our model means our train image, train mask, and all those batch size and the test data that we will feed the training data and testing data to our model. Then finally, when we go for the start the training, what's the we are giving? Keras segmentation train, then path through checkpoints. Path through checkpoints means when the segmentation model will learn suppose you are mentioning checkpoints at 10 or 100. If you want to check your intermediate segmentation result, then you can store your intermediate result in some checkpoints, and from the checkpoints only you can start your segmentation. So, and these are my train images, train annotation, validation images, validation annotation, or you can give test images, state annotation, your number of classes, and what's the model name. Only this much if you will give, then you have already your model, then the model your starts training. Then after your model will trained, then inside this folder, then you have Keras segmentation, then you have predict.py. You have another folder for the predict after the model is trained. So when we run the predict model, here we are giving the prepare the test images. When we are giving, here we can see, here it is my image. This is my predicted output. When I check whether my predicted output is correct or not, this is the infraction it is showing. It's showing, yeah, this part. Yeah, it is the real, actually the infraction is there. So this is actually segmentation is little easy, but to find out the right model and the right backbone is always a challenging in the segmentation that we face, especially in the 2D segmentation, because there is two part, encoder and decoder. So whether it's UNet VGG16 will work better, or UNet efficient net will work better, or a PSP net VGG16 always work better. So that combination, to get a perfect combination, we need to do several rounds of experiment. Actually, we in this Kera segmentation, this is a for the beginner one like you people. This coding one actually, let me find out if I have that folder. If I can find out, then I can show you if this one is good, or means like where you can get that one. Give me a little time. You might think if you ask me some question by that time, I really want to find out this folder for you.
Yes, anyone?
Okay, this one actually is available in the, if someone even if in the search in the Google image segmentation in Keras, this is the folder here you can get. Okay, in this folder here you can see my data set I have already given here. The data set you can see, this is my images. Sorry, maybe I'll show you one after another. This is my images train. These are the brain images. And these are the annotation. These are my test annotations, and this is my test images. And if you go to the code inside the Keras segmentation, here you can see models. In the models, you see UNet is the segmentation model. Here you can just go, and UNet in already they have their layering structure. Okay, and if you want to call mobile net UNet or SNet 50 UNet or the BGG UNet, just now I have shown you, or only UNet also you can call. And if you want to modify also the layers, like the encoded layers, the BGG16, let's say we'll directly go to the BGG16. Here you can see the layer we have discussed about. The past block 1, block 2, block 5, and we are sending this one. If anyone wants to modify anything, wants to modify the number of filters, the size of the filter, or the function, or the padding, or maybe one block, people are now like, why 5 blocks? Why not 4 or 3 blocks? So in some kind of customization, if you want to do, you can just do this one. So when people generally start the segmentation, we always give them this code so that they can play with the code and actually realize what's the like how the coding part can have some effect towards the segmentation. So, and if we'll go for the final predict one, like the checkpoints I have discussed to you, like in every time, like in every epoch, it will give you 1111 checkpoint. So when you will test the model, I think I have this part. When you go to test the model, you can in the predict part, you can just give the checkpoint also, and you can test from that checkpoint. Or you can directly, there is the code is predict.py. They have this one predict.py. Here can also, you can, because this code, why I cannot run, because it needs the GPU. And in the weekend, unfortunately, the GPU is closed, so I can't show you this one. But I have already prepared a code in Google Colab to show you. So this predict one will give you this output. So finally, we'll get to, this is actually the segmentation. So this work actually, and yeah, if you want to get some kind of accuracy, how much you are getting, you can go for model evaluate, and it can predict you like your accuracy is 0.76. This one is like some kind of performance evaluation we can go. This is the work not yet published. Actually, this one is also the non-contrast CT, and the doctor wants to know the severity of the stroke. So here actually we are using, this is the mask, the one, the images, and the mask images after pre-processing, and this is the mask. Then this one here, this is our segmented region. Then you can see this is our final output. Actually, after we are getting segmented region, then we will final superimpose this one. So this one is the segmented output. Like this, here you can see we can know the severity part, how much already red color means already the tissue already like dyed, like the core part, which parts like green color means it is there is a stroke but not yet affected. So to find out the severity or to find out some kind of like shape, the machine we apply this segmentation method. Actually, this is also another example. Here we can see we got the segmentation result. Okay, any doubt? We'll go for the code demo.
Yes, Ayush, Kusagra, people are here or not? Yeah.
Okay, this code actually also I have downloaded from the Kaggle. So this is very easy actually. You guys can also run this one. Maybe I'll send it to you in the chat box. But I know it's in my Google Colab, so you cannot run it here. Okay, maybe in the Kaggle one later I will send you some link you can practice in if anybody wants to practice. So this one like I downloaded the because we need some packages. So from the GitHub, actually I have downloaded some packages from there because this program needs these things. So it takes little time to download. Then the all requirements are satisfied, checking whether we have all the requirements or not. Then TensorFlow, I have import because this code is in TensorFlow. Actually, this code is going to segment the animal. So they have many images and the corresponding mask. Then it is going to animal like whether there is a dog, cat, or rabbit. It want to just segment this one. Okay, from the TensorFlow import. Then they have the data set actually here in the Oxford page. Actually, this one is developed by the Oxford team. So I have just load those data directly from their server. Then you see here I have input image and input mask because well, today morning I have discussed to you, we have maybe certain images of different intensity. They have here used a normalization method. Whatever maybe the pixel, they divided it to 255. So make it like a more normalization one. But they are giving input image and the input mask because for the segmentation we need this one. The data set is downloading because it is taking some time. Okay, maybe I'll teach you the code. By that time, we will run and we'll see the output finally. Okay, so this one is the normalization. Data set is that normalization part is there. Then if we want to do some kind of augmentation in the masking part, then they go for some kind of flipping. So here they have like some left right flipping of the mask. So this one is like some kind of augmentation if you want to use. Then they load the image and the segmented image, then they load. Then this is the batch size. I have already mentioned we need to go for some hyperparameter. This is like some batch size. This one like some buffer size, like at what time, how much buffer at one time you want to show the output. Then this is the steps for epoch. This is like some hyperparameter. Then this is our train and test images we load. Then we load it to the buffer. Then if you want to see some images and their corresponding mask, here you see this is the cat and it's the corresponding mask. I don't know, it's a cat or a rabbit. It looks like a cat. It's a cat. It's a cat. So you can see this is a cat. So it's the mask actually. In that program, they can give it in that this is the mask they have generated. So the program will take this image and this corresponding mask and it will know, okay, this is the shape of the like the image shape of the object. So then finally it will predict the actually a segmented output. Then here you can see they have used MobileNet V2 as the feature extractor. The one we have considered BGG16, they have used MobileNet and input save 128 and this is some layering structure of the MobileNet. Here for the feature extraction, they have used MobileNet. We need to use because we need to download that one and it's finished. And this is the layering structure. If you want to print how the MobileNet layer, this one is the layering structure. Then we go for some like upsample, the one I have already mentioned, and they are using unit model. The one here, you can see unit. And this is the layering structure, some kind of upsample and everything I have already mentioned. And the encoder feature extraction part finished. Then now this is the segmentation model we just call. Now this one is like our hyperparameter. We are using Adam optimizer, and for the sparse categorical cross entropy, these functions I have already discussed in the classification class, and the matrix is the accuracy. Then I run it. The output channels is not defined. Why not defined? I've already run this one. Oh, sorry. I have forgot to output channel, like how much we need. Then this one is the layer. Then we'll go for prediction of the mask. Okay, now go for the SOAP predictions. This prediction is what? During the model training, how the model will predict the mask. This one is the input image. This is the true mask. This is the predicted mask. This one is how during the training, if you want to predict something in between, how like intermediate predictions are there, you can also print like this. Then we go for the actual training. The training one here we can see the epoch, because it will take much time. So I'm just giving epoch is equal to 1. And here the model fit. I am giving my training data and with, as well as my labels. So now the epoch is going on. And for the validation steps, I already told the machine, take the splitting some data from my test sample. Don't take it from my training sample. It will take some time actually. Okay, now it is running, but we need to, because model is training now. So apart from that, I have also considering some concept, maybe you for the performance evaluation. Mostly for the segmentation model, we are using dice coefficient. What is the dice coefficient means? Segmented means you are giving a ground truth or a mask, and how correctly it is predicted your output. Suppose A, you are giving your mask, and B is your output. Like one is predicted output and what is it your ground truth. Then we have the formula, like, sorry. This is the formula. We need to find out the dice coefficient. So if dice coefficient is higher means this value, this A intersection B is, very smaller, means both are overlap to each other, means there is no difference between predicted output and the ground truth. So how generally we calculate? Suppose this one is my prediction and this one should be the target, because target means I always, these are my pixels like 1 1 1 1 1, and these are should be 0 0 0. So how my prediction pixel I got like this after the segmentation, then it will multiply it by the target, then there is some element wise multiplication, then the sum is 7.41. Okay, so this one is the pixel related to prediction related to individual pixel, and this one is like my target. Then the dice coefficient is I put 2 into 7.41 because the A intersection B I got 7.41. Then A cross B means total number of features, total is 16 16, where A and B is 16 represents the number of elements in set A and B. Here we have total 16, here 16, here 16, so 16 cross 16. So here's the dice coefficient is 0.46. Means the main thing is how we calculate this A intersection B. Intersection B is equal to your prediction multiply with your target. Then we go for element wise multiply both of this. Then we got sum of this 7.41. Then after putting this value, we got 0.46. This one is the traditional one, like the dice coefficient we calculated. But some researchers also have some paper just only modification of this part. What they have done, these researchers published in this paper, they said like instead of like this multiplication, how about sum all values of A and B? Means A this value, B is this value. If we summation of this value, this is 7.76. If we summation of all this matrix value, we got the value 8. Then they put their dice coefficient 2 into 7.41. The 7.41 they are getting from A intersection B. And instead of directly give here what we are giving, the total number of elements, here 16 elements, here 16 elements. Instead of giving the individual elements, how about the summation? So here they are giving the summation 7.76 multiplied by 8, and they said is 0.2387. This is also like, you can say, some kind of mathematical research also people are doing. So this is like one option. Another researcher, what they did, they have done, they said instead of the addition, why not the squared sum? So after calculating the a intersection b, they are just square summing all the elements from this a and b, and they are putting this value. Then they are also calculating 0.2368. That is some kind of extra researches apart from the segmentation also people are doing. Here my intention is to show you this one. So now if we go to back to our output, we'll see. Okay, still it is going on. We'll come back to this because the training is still there. Okay, here I also wants to show you some of the papers. Some of the paper I want to show you, some related work, how the segmentation. The one I have shown to you is very simple for the basic one, but exactly in the paper when people are doing, how exactly they are doing. So this is one paper published in the Neuroimage Clinical Elsevier. This is like it is such a more highly cited research paper in our ischemic stroke field. This is the full automatic acute ischemic lesion segmentation. They are using MRI image, actually using convolutional neural network. What's the motivation of this paper? It said when the doctors go for the manual observation, it's like this is actually not a stroke region. This is a T2 sign through effect when images are accurate. When we especially go for this DWI image acquisition, some kind of, we can see in the machine there is some effect. This one is actually looks like a stroke region, but it is actually the false positive. Or maybe the stroke region is like very tiny and it is not really observable to eye. So in such cases, we need AI. And the other mention about like that, when the stroke regions are not, the intensity is not uniform. Here we can see some are darker, some are lighter, some are like more gray. So this is their another motivation. Another thing is like that when stroke regions are there, T2 sign through effects are there, and multiple sizes are there. In that case also, how to distinguish? So to their goal is to stimulation segmentation to minimize and also minimize the number of false positive like T2 sign through effect, all those. So what they have done, first they have considered the data. The data, like they have considered 741 per patients. This is actually paper published by Imperial College of London. So what they have done, they have considered the DWI images and as well as the ground truth. The one I have shown to you using using Label B software, the ground truth. Then after that, they have using some kind of parameters. They have their own network. They name it as EDNet. And they have some of the parameters, learning rate, filter size, stride, and they have split the training and testing sizes. Then how they proceed, they consider the original DWI slice, then they have divided into certain patches, and the size is 64 x 64. So from one image, they have considered multiple patches. And that patches containing ischemic, some patches containing ischemic regions and some are not. Then what they have done, they have mentioned, like here also through this paper, because one student asked me, when he got one image, when got one paper, how to go through this. Here also I want to show you, the paper is 10 to 15 one, how generally we analyze. This one I presented to my guide, like how this paper has been, how the work has been done. So that one also, please pay attention how we can show. When I presented to the paper my guide, so we saw, first we saw the motivation. What's the motivation of this paper? Then we saw, based on this motivation, what's the goal of this paper. Then the entire paper's work we divided into certain steps. Then we showed to our guide, these are the steps followed. Then the step one is the data set generation and the any kind of annotation or anything. Then step one, what is the information? They have information related to implementation, like what's their parameter they have used, which model they have used, how they split the training and testing data, all those things. Then the step two, they have extraction of patches. Then how the patches are generated. Then someone might ask us why they go for the patch extraction. Then from the paper, when we read it, then we show in that way. The first thing, easy distinguish between between normal tissue and ischemic region, because they want to also reduce the sign through effect. And to that part, they say if we consider the whole slice of the image, then the distinguish between the normal and abnormal tissue is difficult for the machine, because when you give the whole total one, it might tell this one might be an ischemic stroke region. Actually, this is the stroke region. This one is the T2 sign through effect. But if you give this one, it might the distinguish of these two things might it is a difficult task. So why not give them certain patches? Then because they said in the patch label to distinguish it more easier than for the machine, they give this reason. Then the second thing is result of larger number of inputs, because they have only 741 patients, maybe 741, there is no huge size of data or huge variety of data. They say if like like if you go for image slices, then the number of data size might not huge. That's why they go for the patch label, so that they can get also very huge number of data. Then the result larger batch size. Of course, if more number of data, the batch size will be higher, so that a machine can learn the features in a more variable way or more variety way. So they have also mentioned they have like for one like the number of patches from one slice they generated 20, and the image patches are used to train the network. But once the model is trained for the testing one, they have just only used the whole image. So the patch is generated for the training purpose, but for the testing purpose is the whole one. So this is the step 2. Then the step 3, the data augmentation, they go for some data augmentation. So what are the data augmentation? They go for horizontal flipping and a random rotation. So here, like from one patch, we can show, okay, they'll go for some flipping and some kind of random rotation. 2 type of data augmentation they have performed. Then they have their own segmentation model. They name it as EDDNet. So what is that EDDNet? It is a CNN architecture that is in ischemic relation by 2 ensemble parallel network, convolutional and deconvolutional. So why they are using 2 network also? We need to say for better accuracy. The goal is to detect all possible probable ischemic region, and the output you will get a probabilistic segmentation map that contains the ischemic region as well as many false positive. Means this is the input image slices. They are generated the patches. They give to the EDDNet, and this is their finally probabilistic segmentation. It is contains the true positive, which is actually stroke region, but also some false positives. And they have using 2 network 1 and network 2. Here we can see why they are using 2 network. They might think one network is not sufficient. Why not the same input will giving 2 network? We generally call it as the ensemble learning. And this one, then after that, both the output they concatenate and give the get the probabilistic segmentation map. Then this is the EDDNet output. Like from here, the ischemic region, they got the true positive as well as the false positive. So here the outcome is the EDDNet identifies mainly many acute ischemic lesion as well as many false positive, which have similar appearance with the lesion. So in this paper, their goal not is to segment the ischemic lesion, but also minimize the false positive, the T2 sign through effect. To minimize that, what they have done, they have go for another network. They go for the muscle net. So they have another one is muscle net. You know, this one is the multi-scale convolutional level evaluation net. So here the goal is to re-evaluate all detection by EDDNet to exclude the false positives, because EDDNet can give you true positive and many false positives. Then this muscle net, the aim is to reduce those false positives. So the output of the muscle net, it will like evaluate whether the lesion is a lesion or a false positive. So that part. So you have your, then how the muscle net work, then the step 5.1, convert the result of probabilistic segmentation into binary segmentation by using thresholding mechanism. The thresholding mechanism we have already learned through say image segment through image pre-processing methods. So they have, this is the output from the EDDNet. Then they apply some thresholding. You see some green color part is there. That part is already gone. So only the red color part. So this one is some kind of binary segmentation they have done. Then they have go for the, after the binary segmentation, they go for the some connected component analysis. So whether, because their aim is to find out it is a true positive or false positive. So they go for the connected component analysis. Through connected component analysis, what they do, extraction of patches around the lesion at multiple scale. Here they have considered 3 scales. For example, from here, from each lesion, from here, then with different sizes, then these 3 patches, they will give to the muscle net and to find out whether it is a true positive or whether it is a false positive. So they combine the multi-scale patches like these patches along with the probabilistic segmentation. Then together they are going to the muscle net. Then this is the muscle net layer. Then it is just like we can say it is a classification layer. Finally, it can say this image is a true positive or false positive. So first they have done the segmentation, got the true positive as well as false positive. To minimize the false positive, they classify the segmented region is a true positive or the false positive. They have considering the segmented region along with the patches they have collected like extracted using connected component analysis. Then this is some result from the proposed method. This is the actual annotation or the ground truth. Then this is the result of EDT net. Here you see it is segmented this part as well as the T2 sign through effect like the false positive. But after EDT plus muscle net, this part is already gone. So each one is only the true positive one. Like this. Here we got 2, then after muscle net only 1. So, but then after this, so this one how we generally, when we got a paper, we analyzed this paper, we made a PPT like this. Then after this, of course, every paper has the limitation. Then why we will go for our work? Already if paper has done the similar work, then we go for our limitations. What we found, this method also result many false negatives. False negative means ischemic region is there, but model cannot detect because model might think it's a false positive and it cannot detect. For example, this one is like already annotated means it is a true positive. It is also an ischemic region, but model thinks it is a false it is a false positive. So model cannot detect. It can only detect one stroke region. So this is one limitation for us. The second one we found, the muscle net works well when FP size is small. Means if the false positive size is small, it works well. But the false positive size is big. For example, this size is very big. Okay, so this one actually in this case, muscle network will not work. Even if it is a false positive, even if it is a T2 sign through effect, but if the size is bigger, so it cannot say it is a false positive. It is say it is an ischemic region. So this is some kind of we, generally analyze the paper and we made a PPT like this and we presented, then we saw some limitation. So this is somehow we are like analyzing if it is medical related paper. Then if we have some like analysis paper, then that is another way of presentation. Here just I want to show you the segmentation. Like here the machine not only go for the segmentation, even after segmentation to minimize the false positive, they have go for another round of experiment. So this is how people are doing the work. Let's back to our code. You see, after one round of epoch, we got this is our true mass, this is our predicted mass. The machine is predicted like this because I just give one epoch, so it's just like this. Let's see, considering this one, we'll predict some test result. Because I just give one epoch, so we just give one dot. But if I'll give multiple epoch, then you can see a graph clearly actually. Then if you see some of the predictions. You can see for this dog, this one is actually the true ground truth. Our machine is predicted like this. This is the cat, machine is predicted like this. So if we go for more epoch, we can get a better accuracy and like this. So this is like one demo I want to show you how the segmentation model really works. Any questions?
Yes.
If no, then I have another.
Yes, any questions? I think you can continue. Hello.
Okay, this is another related work. Here, actually, my intention is to show you one student asked us if more number of convolutional layers, then there might be an increase in accuracy or what. So how can we do some kind of experiment? So I'm going this paper through fast. Here, I just want to show you how people are doing the work. This one is some kind of stenosis detection. Stenosis is just like the artery which is connected from our, connected to our brain. Sometimes because of some thicky substance or maybe some plaque is deposited, so the artery is narrowed down. So the right amount of blood cannot flow. So that problem we generally call it as the stenosis image. So this image actually is an X-ray angiography image. We have discussed about CT, MRI. This is an angiography image. So how much narrowness or whether there is a real narrowness or not, doctor propagates angiography image, the image quality is not at all good. So doctor cannot see whether that is a true narrowness or not. So because the low contrast level, and also the diagnosis varies from doctor to doctor, because here this one is a narrow, doctor can see this one is a stenosis. This doctor might say this one is little narrow, maybe this one is a stenosis. So that one is also a problem, whether it is a real stenosis or not. So for this one, this paper also go for some kind of image analysis. What they have done, they go for some pre-processing. In the pre-processing, what they do, this the rescaling of the image to do they from 256 to 256, they reduce it to 128 to 128. Why? They reduce the amount of data for lateral processing and simple method of denoising. They have just mentioned these two they have mentioned. So then they said because of the rescaling, denoising means what? Because they said the surrounding one is like contains some kind of noise, the background noise. If they will reduce the size, this background part is detected, sorry, the deleted. So the background noise, they said, like the background arteries, small arteries, it will be deleted. So that some methods they have using rescaling method. Then the same, they go for the patch generation. They generated a patch size of 32 cross 32, and the number of patches they have extracted 250. And while they are generating the patches, they generated some patches with artery, and they have generated some patches without artery. Actually, then they go for some artificial patch generation because they don't have the exact data. Sometimes the data size is we have not very high, and it's difficult to get the data. So they go for some synthetic data generation. So they have their own model to go for some synthetic data generation. They generated 10,000 data from 10,000 patches from that. So they have give like some natural image and artificial image data. Then they go for architecture. They go for 6 types of CNN architecture. That actually my intention to show here. How can also we go for the experiment? And these are like some parameters like path size, epoch, momentum, and all those things. Then they give those images to the CNN classifier to find out whether it is a real stenosis or no stenosis, because doctor confused which part is a real stenosis, which part is no stenosis. Then here the main highlight point, why they go for 6 CNN, because they don't know which combination gives them the better accuracy. So to selection of a suitable CNN network, first they make only the two fully convolutional layers like FC1, FC2. They have used the two dense layer only, they have considered one. Then they have considered only two convolutional layer. Then C, three convolutional layer. Then D, three convolutional layer with little modification. Then E, they have considered three convolution, then a max pooling layer. Then in the F, they have using four convolution, then one fully connected layer. This is like some kind of combination also we can do, or we generally do also to get the better accuracy. Then after that, they find out with the fully connected layer, the network A and the network F, which they have connected with 3, 4 convolution and FC, will give them the better, generally giving them the better accuracy. So they have now two, like the least one and this one, they have considered. Now they retrain it. Then how they retrain it? They have also considered artificial generated patches plus real patches. Then they have using these things, this training and validation parameters. Then when they are checking A and F, they are finding out, okay, with the F1, they are getting very good accuracy, 0.74 and 0.90. So that actually the thing. So here also, when we have presented to our guide, then we have also some kind of limitation of the paper, because they have considered very less number of data. Even if they are go for the artificial data, what's the problem? And although they'll go for the patches, but there is no template matching algorithm. So how they know which patches are from the which artery? That part they have not discussed. So that's the thing actually. But here my intention is to show you we no need to follow a particular CNN layer. We can also go for some addition of layers, deletion of layers to improve the accuracy. So thank you. If any question, please ask.
Yes, I.
Ma'am, Like, I just wanted to
Mm.
talk on the project that you are working, that food one.
Okay, the
So,
previous one. Okay.
yeah, yeah. So basically, I mean, someone asked about that if it is prepared by two different chefs, then the nutrition value will differ. So
Mm-hmm.
I was just thinking on that, that at the last, camera is also a type of a sensor that basically takes the light, forms the image, then it is fed to the model, and accordingly the model
Yeah.
predicts. So why just only depend on the camera? What if we use a certain kind of a sensor beside that, that can like bombard several wavelengths of light of various intensity, and
Mm-hmm.
it just receives that reflected light from the food and then analyze that. I mean, because different elements signs accordingly. I mean,
Yeah,
like,
that yeah,
analyze the color.
yeah, that also okay, but that one also vary. But because that PPT, if I'll show you the one you are saying, yeah, that can be one of the solution. But we need to see if all a solution is feasible or not.
I mean, like, presence of too much oil or sugar or freshness.
That one, for example, when the images are taken, because the camera is not like it's like somewhere upon that one is fitted. So you say different intensity. That all different wavelength, different intensity. That one is bombarded. That one, but to buy that camera to one, we need to like expend some money, spend some money.
Yeah, yeah.
Another thing is that wavelength, because the food color also, and every day it's not like the cabbage look like this. You see, maybe today the
Mhm.
cabbage look like this. Sometimes the cabbage is overcooked and sometimes the cabbage is undercooked also. So it's not like from that one only that intensity. So how many intensity we will fix for that camera? How many wavelengths we need to fix? Because each day there are different type of food. Even if using the cabbage also in Taiwan, they have 5 to 6 cabbage with carrot, cabbage with egg, cabbage with shrimp, cabbage with fish they have. So that one also a mixed thing. So how many wavelengths we need to fix? That's first thing. Second thing is we need to go for that. We need to go for very high resolution or very high technical camera. So who is going to pay that money? That's the second thing. And third thing is like that. For that image taking and image processing, it will take some time, because if multiple images will go, we need very high sophisticated backend server that needs to be run. And because when the person we are checking the food, many persons are there behind. So we cannot spend 2 3 minutes or 4 minutes on for one person. It's just like the image will taken, because with this one we have second, we got the output within 20 seconds is the max. So and then maybe just check the value, how much fat, how much that one, then within I think less than 1 minute, 1%, our target was to achieve that one. So if that processing will be done, it will be take another time. So there are some constraint also there. We cannot go for like a very high sophisticated technology. But
Yeah,
yeah,
I
the
mean,
solution, like, yeah, the solution can be considerable, but also we need to think this solution is feasible to here or not. Okay.
yes, I mean, it will get too costly for this, I think.
Costly and timing. Yeah, another
Yeah.
thing, timing. That also a very important thing, especially when we go for a real time one.
Yeah, I was just thinking like any kind of
Yeah, yeah,
solutions
yeah.
can be done
Yeah,
with
very
that.
good. If you are thinking something out of the box, means you are in the right direction, because you always need to think something out of the box for the research and development. So
Because
that's great. Keep it.
it just came into mind because
Yeah,
as
yeah, that's
the,
good. That's good. Yeah,
I
yeah, that
mean,
could be one solution. That could be one solution. That solution, maybe we can consider maybe some kind of, like our border detection, maybe border, be an enemy is coming or something. Uh, someday people are using different, disguise methods to come, so we
yeah,
can find out different color intensity, and some kind of border security we can apply, because here cost is not a problem. Here like we can get very good backend server, and also it's not like a real time, because the border camera is just like 24/7.
yes,
Even if
yes.
little delay also fine. So in that case, yeah, it's applicable, it's a good solution. Yeah.
Yeah, I just like I thought in terms of like as CT scan and MRI, they doesn't, I mean, differentiate between a black people and white people. It just gives the interior parts in that. But I
Yeah.
mean, it will work, but I think like it will get too costly for such things. I mean, it's
Yes,
kind
yes.
of
And
high
And you
processing
know,
hardware.
always in medical things, the doctors and the governments always wants us to take the like less expensive solution, because we don't want to put so much burden on the patients to give money. So with
Mhm.
less money, if the things can be done, then they will prefer that.
Okay, ma'am, I got it. Thank you, ma'am.
Okay. But thank you for your inputs. Yeah.
Yeah.
Yes, Kusagra, last question from your side. Yeah.
Ma'am, what was I think the main reason for choosing CNN architecture A and F in the last PPT you
Mhm.
showed, that this one, because for
Mhm.
the
Yeah.
final retraining stage mainly gives the better accuracy, or other there are some other factors also.
Actually, when we go for here some kind of analysis, actually it is a conference paper. Here my whole intention is to show you uh, how we can go for selection of the model. Suppose you will take a BGG 16, it is actually 16 layer. One student asked me, if we, I think the classification class, if we take all the 16 classes is good, or we can delete some of the 16 layers is good, or we can add or delete some layers, whether there is an impact to the accuracy or not. I said, yeah, there is. How we can see there is an impact or not? With less number of layers also, sometimes we get better accuracy. With higher number of layers also, we can get better accuracy. So that we can only go through bit combinations of layers, that we can go through hit and trial method actually. So here my intention is to show with many number of combinations. Here they have seen, even if with less layers, even if with higher layers, they are getting some accuracies. Then how to know which one gives us the better? So it's some kind of experimental way to find out the suitable CNN model for our data. So that's the thing.
Okay, ma'am.
Yeah. Because we don't know, we are like we are also black box. I told you to take BGG 16. You might ask us, why ma'am BGG 16, why not efficient, why not resonate 50? And if BGG 16, why I will consider all 5 blocks? I don't want to consider 5 blocks. If within 4 blocks I will get better accuracy, then why there is extra block? It will take the computational resource, time resource, and the time complexity also very high. So now people are also doing the experiment, the many good research papers in that way. This is just a small paper I just shown you, but reducing the network size, reducing the feature size, reducing the filter size, the impact. Because my last PhD paper actually related to that. How to reduce in the feature map, how to number of filters will improve the accuracy with less computation. Because it's not yet published, because busy in postdoctoral and company work. So not yet published. We are in the communication stage. But yeah, my whole intention is to show you this one. Yeah.
Sure, ma'am.
Yeah.
ठीक है जी मैम. Any questions from your side or we'll stop? ठीक है जी मैम, हाँ ज्वाइन कर.
Okay, if no question, then it is really very nice to take this session. Tomorrow I have one session and one with Dr. Gupta and with me together. Yeah, for that tomorrow second session where both Dr. Gupta and I will be there. Actually, on that place, please prepare some questions to ask us, and some feasible questions that we can answer. And yeah, and another thing, like the last night, Dr. Gupta has shown you
And
some
also we'll take
radiomics thing.
the verbal feedback also. Total means how was this total winter school?
Yeah. That one, yeah, very much important. And if you have any questions or anything from the, you can go through our like again the videos and have a check. If you have any question or anything, so we are happy to
And
take
I
those
will also
questions.
request to Dr. Sulagna and Pushpa prepare some assignments so that we can give the students, so we can give 7 to 8 days time to complete that one. So that is also one of the criteria to select the participant students.
Yeah, that one also we both will discuss and will prepare
To
it
just
accordingly.
I will also
Yeah.
call you today evening or tomorrow morning also. So
I think
we'll,
better, sir, tomorrow we will
yes,
discuss,
yes,
because today we have some other arrangements.
yes,
So
yes.
tomorrow we'll discuss about that after, because after all session will over, then better we will discuss it with tomorrow. And yeah, within this 7 days winter school, like thanks a lot, Professor Das. Like you have really took a very good initiative for the starting one. Honestly, when Dr. Gupta and I we started the work, because we are both PhD mates. So when we started at that time at the year 2018, there was nobody and no resources there to even if what is the classification, we really don't have any idea. So at that time, nobody is there to tell us because everybody is new. We are new, our guide is new, everybody is new. So we learn from the experience. Actually, we learn from the failure experience, I can say. So from 2018 to 2000, it's 25th. So 25, so already 7 to 8 years, we can say. So still we are learning every day and learning from you also, people, because you are also saying, asking us some questions, and we are, so it's not like it is.
And during MS also, your domain was different.
Yeah, in my master, actually, I have work on cognitive radio networks. My 2 publications are actually, that one is related to that, and Dr. Gupta's work was in cloud computing in MS. So yeah, so that one we are from very different background, we jump to here. But that one is also, from your background and your current work, also very much like helpful, because what Dr. Das has mentioned, my master was on networking, my PhD is on medical data analysis using artificial intelligence, my postdoctoral also using the liver data, MRI data analysis. But currently my job, because now I am in a new job in a managerial position, so in that position, my my company is a networking company actually. So now we are applying AI in that networking things. So it's some kind of, fusion. So that one also, even if you are gathering knowledge from one domain, you can also apply it to another domain. Pre-trained model, the one I have already taught you last week. So it's not like you only use these things in the medical data. Even if the other applications, other concepts, you can also use the same thing. So no worry.
Okay, thank you very much. All of you just join at 3 o'clock for Dr. Nikul Raut of nephrology. He is
Yeah.
going to talk about 15 to 20 minutes.
So yeah, so Professor Das, at what time the cultural program will start?
3:30, 3:30.
3:30. Okay.
Okay.
We'll try to
So
be
those are
there.
expected to join there also. Okay. Thank you very much.
Yeah. Thank you. Thank you, all of you. Thank you.